Okay, so without further ado, let's start our class for today. Okay, we are in the previous class, we already finished how to calculate how to get the IEEE 754 format, okay, for a double precision and single precision. Okay, now we're going to look at this, what we call here, variation of IEEE 754 format out there. Right, so here are the format we have. There are 6 formats that you can find in the IEEE 754. Okay, which is the first one is a half. Okay, so half is for only 2 bytes. Okay, which is 1 is for sign bits and 5 is for exponent bits, and the significant bit or the multi-side is 10 bits. For the bit float, okay, also 2 bytes. Okay, and then you can see here the exponent is bigger compared to the mantissa. All right, and previously we already looked at the single precision and double precision, which is consists of 4 bytes for the single precision, while double precision is a 8 byte. So 4 byte is equivalent to 32 bit of data, and 8 byte is a 64 bit of data. And then apart of that, we have the double extended, okay, which is greater than 10 bytes. Okay, so 10 bytes will equivalent to, if you have a 10 bytes, okay, it will double this number here. All right, equivalent to 1328, if not mistaken. Yeah, 128, and then we have the quad byte, which is total of 16 bytes. So this is the total of sign bits, exponent bits, as well as the significant bits. And here are the advantage lah, okay, by using a single precision and double precision, okay, which is the difference between the single and double precision. Okay, for the single precision, okay, 32 bit are used to represent the floating point number. Okay, for single precision, okay, we allocated 32 bit, okay, to represent it. 1 bit is for the sign, 8 bit is for the exponent, while 23 bits are for mantissa. Okay, meanwhile, for the double precision, a total of 64 bits are used, okay, to represent a floating point number. So it's more precise lah compared to the single precision. It uses 11 bits for the exponent, right? And then for the mantissa, total of 52 bits of mantissa. Okay, regarding the bias number, in order to get the exponent here, okay, we need to add with the bias number. Okay, the bias number for the single precision is 127. Meanwhile, for the double precision, the bias is 1023. So this is 1023 is actually depend on the how many bits of your exponent. All right, since 11 bit for the exponent, so the bias must be 1023. Meanwhile, for the x bit exponent, the bias is 127, and this is the range lah of the number in the single precision. Okay, and this is the range for the number in the double precision. You can see here 2 power of minus 126 until 2 power of plus positive 127. Right? And in the single precision, okay, most commonly used when the precision matter less lah. Okay, but the precision still need to be there, okay, compared to the fixed point. Fixed point means that more or less precision, okay, compared to the floating point. And for the double precision, use where the precision matter more. Okay, and for single precision, use for the wide representation, and this is a use for the minimization of approximation. Okay, and in terms of applications, so this single precision is used in a simple program like games. Okay, and meanwhile, double precision is used in complex program like a scientific calculator, because the scientific calculator, the precision is matter. Okay, and that is for the single and double precision. And here are the difference between the fixed point and floating point in terms in the microprocessor. Okay, in the fixed point is, if we use a fixed point, okay, so if we okay, it is less accurate lah compared to the floating point arithmetics. Okay, and the range of the value is smaller lah. Okay, which is previously we see the range is somewhere around thousands, okay, 100 or 1,000, but this one here, the range is more than 1 million, okay, from positive and negative 1 million to positive 1 million. All right, so usually, okay, the fixed point is used in a built-in circuit. Okay, for the floating point, also used in a built-in circuit for software implementation, or hardware. For the hardware implementation, we need to use this FP unit. FP unit is a floating point unit. Okay, and if you use the floating point unit, means that the cost of your hardware will much expensive lah. Okay, because we have external circuit here. All right, and when we're going to use a fixed point, and when we're going to use a floating point, to the fixed point used when the cost or power is more important. Okay, so if you're going to build a system or build a device which have low cost power, okay, low cost and low power consumption, okay, better you use a fixed point arithmetic, which is your device, okay, the accuracy of the device is not so important, okay, so you can use the fixed point arithmetics, okay, and the floating point arithmetics. So when the accuracy is more important, then you need to go for floating point arithmetics. Okay, so that is for the fractional number. Okay, for the fractional number, we already learned about the fixed point and floating points. Okay, now we're going to look at the input-output codes. Okay, so in computer system, okay, this most of the computer system use a codes, okay, to represent either a numbers, to represent a characters, or to represent simple symbols in a format that can be stored, processed, and transmitted. So the most common coding code system are binary code decimal, a BCD, ASCII code, Unicodes. Okay, so now we're going to look at what is a BCD. So this is the most common lah. Okay, binary code decimal, a BCD. So BCD is a class of a binary encoding where each decimal digit, okay, from 0 to 9, is represented by a fixed number of a bit, typically in 4-bit representation. Okay, so this BCD is commonly used to drive the 7-segment display. Okay, by using a BCD, we can directly drive the 7-segment display to display the digits, okay, from 0 to 7. All right, so this is the codes and the BCD codes, and this is the decimals lah. Okay, in order to display 0 on this 7 segments, right? So we need to give a 0, 0, 0. Okay, so it will display 0 on this 7 segment. But of course, in order to use this binary code decimal, okay, we need to have a decoder. Okay, so this decoder is used to translate from the code that you given here to drive the LED of the 7 segment. Okay, if you recall back, the 7 segment consists of 8 LEDs. Okay, it's represented by 8 LEDs. A, B, C, D, E, F, G, and then H for the decimal point. Okay, so here, what happens if you're not using this decoder? Okay, if you're not using this decoder, how to represent a number 3? Okay, how to display a number 3 on the 7 segment? So to display a number 3, okay, you need to turn on. Okay, you need to turn on LED A, okay, B, C, D, G, and That's it. Okay, A, B, C, D, G, while F, E, and H must be turned off. So now number 3, okay, number 3 is displayed to the 7. So now to turn on this LED, okay, we need to give a number value. Okay, so that each of this LED is a turn on and F, E, and H LEDs are turned off. So how to derive the numbers here? Okay, based on this uh, uh, LEDs, okay, we arrange the LED as A become the least significant bit, while H is the most significant bit. So you give A, B, C, D, E, F, G, and H. So H is a NSB. Okay, assume that, okay, because the what we call here the 7 segment have 2 configuration. Okay, one is a common cathode configuration, and the other one is a common anode configuration. Okay, for the common cathode, in order to turn on the LED, you need to give 1. Okay, give 1, LED will turn on, and when you give a 0, the LED will turn off. Okay, compared to the common anode. So common anode means that, okay, I forgot to tell you, for the common anode, okay, all of the LEDs, all of the positive LEDs are connected at VCC. Okay, and the negative terminal is connected to your microcontroller. Okay, so in order to turn on a common anode, you need to give 0 to your microcontroller, so that since this is a VCC, okay, the VCC means it's a logic 1. Okay, when logic 1, okay, when you give a 0 to your microcontroller or your microprocessor, so what happened here is, okay, there is a difference, okay, from high to low, okay, from VCC to here. So next what happen, the current can flow across the LED. So the LED will turn on. Okay, so for the common anode, to turn on, you need to give a 0, while off, you need to give 1. Okay, what about the common cathode? Common cathode means that all of the negative terminal is connected to ground, and the positive terminal will connect to your microprocessor or microcontroller. So now we're going to find out what are the value that need to drive LED A, B, C, D, and H, so that it will display number 3. Okay, we assume we use a common cathode. Okay, the common cathode means that to turn it LEDs on, give 1. So A, okay, you need to give 1. B also 1 because the B is on. C on, D also on, E off, F also off, G on, and H off. So now here you can see, so this is the number that you need to give, okay, which is F4F in hexadecimal. Okay, by giving a 4F to this 77, then after that, the LED will turn on. But by using a binary code decimal, okay, with the help of this decoder, so what happened, you just to turn on number 3, okay, to display number 3 on the 7 segment, you just give this code 0011. Okay, 0011 is actually equal to 3. If you convert this binary number to decimal, it is actually equal to 3. So by using the 0011, okay, put it to this decoder. So what happens? This decoder will drive this number. Okay, so it will provide this value 0, 1, 0, 0, 1, 1, 1, 1 to this 7 segment. Then the 7 segment will drive the LED accordingly. Then the number 3 will be displayed on this LED. So this is what happens. Okay, so now let's say you're going to display 3 to 7 on the 7 segment. Assume that, okay, you have a decoder And now we're going to find out what is the binary code decimal that you need to give. Okay, so the binary code decimal that you need to give for 3 to display 3 to 7 is a 0, 0, 1, 1 for 3. 2 is a 0, 0, 1, 0. And 7 is 0, 1, 1, 1. How do you get this number here? Okay, based on this binary representation, which is by using the 8421 method lah. Okay, by using the 8421 method, then you know what number that you need to give in order to give to the decoder in order to display that digit on the 7th segment. Okay, so this is the number, okay, that you will give. Okay, contoh, this is the code that you give, and then from this code here, it will send it to the decoder, and the 3 to 7 will be displayed on the 7th segment. Right, so this is a binary code decimal. Okay, very simple code out there. Okay, then we have the ASCII code. So the ASCII code is an American standard code for information interchange. Okay, which is defined binary pattern for letters, either a capital letter or small letter. Okay, symbols, numbers from 0 to 9, or a device control code such as a spacebar, enter, delete, okay, and etc. So for the ASCII, only 7 bits are defined by the standard. Okay, because by using a 7-bit, you can display all of these letters here. Okay, started with a capital letter and small letter, and a symbol such as a alias symbol, hashtag symbol, apa lagi? What else? Comma, semicolon, ampersand. Okay, we have a symbols there, and then to display this digit from numbers from 0 to 9, and other device control code. Okay, so a total of 7 bit is enough to represent that. But normally, okay, we append with a 0 to make it 8 bits. Okay, for simplification, okay, we just use a 8 bit. So what happened? All right, the last bit we just the most significant bit we append with 0. So this ASCII represent letter for American English only. Okay, if you're going to use for the other language, such as if you have an Arabic language, okay, you have Japanese character, Chinese character, or other characters, okay, you need to use another code called a Unicode, okay, to display that character. Right, so this is the ASCII code chart, right? So here, this is the special function that I told you earlier, okay, such as delete, okay, and then spacebar and so forth. All right, then this is the symbols, okay, and this is the capital letter, right? Capital letter. We have another symbols in between, and then small letters. And last but not least, we have a symbol. Okay, and here you can see, okay, this code is in using the hexadecimal value. Okay, you can see this is from 0 to 7. This is from 0 to F. Okay, for example, here, I'm going to press A on my keyboard. So what will be the code that will be sent to the processor? Okay, so capital A is actually here. Okay, so when you press the keyboard A, actually this number will be sent to your keyboard for 1. Okay, so when 41 is sent to your processor, the processor knows, oh, okay, now A is pressed. We need to send A to the monitor. So 41 is actually represented by A. Okay, let's say lah, if you're going to represent the MKEL. So the ASCII code for M, K, E, and L is, where is the N? So this is an M. Okay, so the code is for B, for M. K, capital K. Capital K is for B. Okay, then followed by E, capital E, okay, for E, sorry, for 5, and L is, where is the L? Here, okay, for C, right? So when you press this MKEL on your keyboard, this number will be sent to the processor. Okay. Okay. And now, okay, we move on to the parity. Okay. So a parity bit is an extra bit added to the binary data stream, okay, to detect error in data transmission or storage. Okay, so why is parity bit is important? Okay, when you send a data over a network, okay, there is a chance that that bit may be flipped due to the noise. Okay, so if you have if there is a noise on that network, okay, the bit will be flipped. Okay, from 0 to 1, 1 to 0, or interference or some of the hardware issues. So this parity bit, okay, will allow the system to check, okay, if data was corrupted during a transmission. So this is why we need to send a parity bit to check whether the correct data is sent through a network and the receiver get the correct data, right? So there are two types of parity bit. Okay, one is we call it as an even parity. Okay, the parity bit is set so that the total number 1 is even. Okay, so that is the even parity. And the odd parity, okay, which is the parity bit is set so that the total number of 1 is odd. Okay, for example, here. Okay, so this is for the even parity examples. Okay, so let's say, okay, this is a decimal value, and this is the number, binary number, and this binary number you're going to send it, this number here, the decimal number, you're going to send it to the networks, okay, through the networks. So first, what happened here is, okay, the decimal number will be converted to binary representation, right? So this is a binary representation. And if you include the parity bits, okay, there will be 1 bit for the parity, okay, to check whether the data got error or not. So how you going to determine what value that you need to give to this parity bit? Okay, let's assume we using the even parity now. Okay, so for the even parity, for bit 0, you can see here, 0, there is no number 1 in this bit. Okay, so that's why the parity is 0. Okay, for number 1, you see when you count the number here, the ones in this number 1, okay, it only has ones, okay, which is odd. So you need to make it even. So that's why the parity you need to put 1. When you have 1 plus with 1, now you get 2, a total of 2 ones. All right, so now the value is, the total number of 1 is even, right? Meanwhile, for number 2, you can see here from number 2, when you change from decimal to binary, so this is the binary representation for number 2. When we count ones, okay, we only have 1 once. So what happened? We need to make it even. So we plus with 1 to the parity. Okay, so now it becomes, okay, now this number here already have it in even parities. All right, for number 3, you can see here when you change from 3 to binary, okay, the value is 1 1. Okay, 0 0 1 1. When we count the number 1, the total of number 1, okay, 1 2. Okay, so you will already have the even number of number ones. Okay, total the even number of total ones here. So that's why the parity is set as 0. Okay, what about number 4? Number 4 only have one, what we call here, 1 ones. So next, to make it even, you need to put 1 to your parity. Number 5, we have a total of 2 ones, so no need to give a parities here because the total number 1 is already even. All right, number 3 also same lah. Okay, we have a total of 2 ones, so that's why it becomes 0. What about number 7? Okay, when you change 7 to binary, you will get 0, 1, 1, 1. So when you count up this one here, you have a total of 3 ones. Okay, so to make it even, you need to add another 1 to the parity. So now you have a total of 4 ones. Okay, so number 8, you need to add another parity bit here. You need to set the parity bit. So total number of 1 here become even. And number 9, since the total number of 1 is even, so no need to put a parity. Okay, so this is how the data will be sent, okay, through the network with a even parity. Okay, for example, if you have an ASCII, okay, same thing lah for the ASCII. All right, so for the ASCII, let's say lah we have a SALAM, salam, and this exclamation, this punctuation marks. Okay, so here now S. Okay, we go back, look at the what we call the ASCII table. Okay, capital S, where is a capital S? This is a capital S. Okay, the value is 5, 3 for the capital S. Okay, we just write down here 5, 3. Okay, when 5, 3, you change it to the binary representation by using a 8421 method lah. Okay, 8421 method. 5 is a 0, 1, 0, 1, and then 3 is a 0, 0, 1, 1. Okay, and recall back. Okay, the ASCII is only up to 7 bit. Okay, so that's why this bit here will be discarded lah. Okay, so now we're going to find out how many ones in this here. Okay, example, we are using the even juga kat sini. Alright, even parity example. So 1, 2, 3, 4. So we already have 4. So what happened here is, okay, the parity bit will give 0. Okay, so this is for the even lah. Okay, and if you use odd parity, so the parity bit is you need to put 1. Okay, because the total number of 1 now is even. Okay, to make it odd, you need to put 1 to the parity. So now it becomes 5, which is a odd parity. Okay, what about A? Okay, so now we're going to look at A lah. A, what is a small a? Small a is a 6, 1. Right, so we have a 6, 1. Okay, change it to the binary representation. All right, so we get 1, 1, 0. 1 is a 0, 0, 0, 1. Okay, when we count now, okay, we have 1, 2, 3. So now it's a odd number. So to make it even, so the parity here, we need to give 1. What about if you use a odd parity? So the parity will be 0 lah. Okay, because the total number of 1 is already even, right? And the rest will be same lah. Okay, you need to look at the character. Okay, what are the ASCII codes for this character here? Then after that, find out the total of number 1. Okay, if the total of number 1 is not enough to make it even, so you need to plus with 1. If not, if the total number of 1 is even, then you give 0 to your even parity. Okay, and the last slide here is for the Indianness. Okay, so this Indianness is very important when we dealing with when we're going to store a data inside of the memory. So what is the Indianness? Okay, so Indianness is the order of how the sequence of a byte of a word is stored in the memory. Okay, how you're going to put the data, okay, from CPU to the memory, right? So we have a total of 3 Indianness here. Okay, only that, okay, the most common one here is either big Indian and little Indian. Byte Indian is not commonly used in computer system. Okay, so what is a big Indian? What is a little Indian? So the big Indian, store the most significant byte of a word at the smallest memory address. Okay, means that you have a most significant byte from the data. You're going to store it at the lowest memory address, at the smallest memory address. Meanwhile, a little English says that store the least significant byte at the smallest address first. Okay, so this is a illustration of the big Indian and little Indian. Let's say lah, okay, we have this number here, a 32-bit number. Okay, from this 32-bit number, we are going to store it inside of this memory. Okay, and this memory is a 8-bit configuration. Okay, 8-bit configuration memory. Okay, now, so how we going to store by using a big Indian and how to store by using a little Indian. Right, so first, what you need to do here is, okay, since it is a 32-bit numbers, okay, we need to divide it to 4 bytes. Okay, 4 byte means that 8-bit by 8-bit. Okay, so you need to, from 32-bit numbers, you divide it into 8-bit groups. Okay, so this is 8-bit groups, 8-bit group, and 8-bit group. So we have a 4 bytes here. From here, we identify, okay, which byte is a low, least significant byte, which byte is a most significant byte. So this is a least significant byte, and this is a most significant byte. Right, now we are going to look at the memory address. Okay, so each of the memory, okay, if you're dealing with a memory, we have a memory address here. Okay, and assume that this memory address is 1000, 1001, 1002, 1003. So that's why you can see, okay, here is A plus 1, A plus 2, and A plus 3. Okay, now what we need to do? Okay, since this is a bit Indian, okay, a bit Indian says that most significant byte, okay, will be stored inside of the smallest memory address. So this MSB AA will be stored at address 1000. Okay, then followed by BB at 1001, CC at 1002, and DD at 1003. Okay, so this is the case for the 8-bit memory configuration. Okay, we have two types of memory configuration. Okay, one is a 8-bit memory configuration. Okay, memory. There are two types of memory configurations here. 8-bit memory configuration, 32-bit memory configuration. Okay, don't get confused. Okay, what is how to store data to 8-bit memory configuration and 32-bit memory configuration. Okay, for the 32-bit memory configuration, okay, assume that this is your memory. Okay, now the memory size is a 32-bit. Okay, so this is a memory configuration, 32-bit memory configuration. And here, let's say like this is a 1000. This is a memory address of 1000. And the next address will be 1004. Then 1008, and then followed by 1006. Okay, why is that? All right, because, okay, for 32-bit, how many bytes we have? 4 bytes. Okay, so actually, in address 1000, we have 4 bytes of data. Okay, 4 bytes of memory here. Okay, so this is at 1000. This is memory 1001. This is memory 1002. This is memory 1003. And then next will be, here will be 1004. And it will keep repeating lah. Okay, only the configuration of the memory configuration is different. Okay, this one is a 8-bit. You can see 8-bit quite easy lah, because okay, you add with one byte by 1 byte. Okay, but this one here, 4 byte by 4 byte. So you can see here, from first memory to the second memory, you need to add with 4. Okay, next is another add with 4, add with 4. And actually inside here, you have a 4 byte of a memory. right? So how you going to put the data? Okay, by using a bit Indian. Same thing juga. Okay, the same thing applies. Okay, which is the most significant byte. Okay, will go to the lowest memory. Okay, the smallest memory. So AA will be stored here. Then followed by BB, CC, and D. Okay, so this is what happens. Okay, same thing. Only that the configuration is different. Okay, yang ni we look at 8-bit, but this one is a 32-bit configuration. Right. And next we look at the Little Indian. Okay, we have the same data, but now we are going to store, okay, by using a Little Indian. Okay, so same thing. You divided this 32-bit number into 4 bytes. Okay, then we have the LSB and MSB here, right? Then after that, so assume that this is the same address lah. Okay, 1000, 1001, 1002, and this is a 1003. Okay, so what happened here? Okay, for the Little Indian, it says that store the least significant byte at the smallest address first. So you have take this least significant byte, okay, from this data, store it to address 1000. CC go to the 1001, BB at address 1002, while AA at address 1003. Okay, now you can see the sequence is different. Okay, by using the bit Indian and Little Indian. Okay, what about if you use a 32-bit configuration? Yang ni 8-bit ya. This one is a 8-bit configuration. What about if you have a 32-bit configuration? Okay, 32-bit configuration, same things lah. Okay, you have 1000. This is a 1004. Okay, what you need to do here is, okay, you divide it into 4 bytes. So this is actually a 1000. This is a 1002. Oh, sorry, 1001, address 1002, and this is the address 1003. And how you going to put this data to this address? Okay, so takes the least significant bit, byte of data, put it at the smallest address. So DD go there, followed by CC, BB, and AA. Or you can copy directly this number, put it inside of this address. Okay, so this is by using the Little Indian. Okay, so don't get confused. Okay, sometimes, okay, in the books they are using the 32-bit memory configuration, and some book will use the 8-bit memory configuration. But the way we're going to store the data from the register or from the CPU to the memory will be the same. Okay, depending on the Indianness that you're going to use, either a Little Indian or a bit Indian. Okay, and for the ARM processor, okay, they are using Little Indian. Every time they're going to store the data from the CPU or from the register to the memory address. Right, so that's it for this module 0. Any question from you guys?